Good morning, everyone. We will begin the webinar in a while. We're just setting up the YouTube feed. Okay, seems everything is online. If there's any problem with the audio, please let me know on the chat and I will move ahead. Good morning, one and all. Today, we are fighting a pandemic, but this pandemic should not disable us in any way or come in between one's learning process. And to make sure of that, we at the Department of Physics, PPC and PAC are organizing this webinar to help you all and all those interested in knowing the opportunities in space science and astronomy. From the motivation of the success that came from our online workshop on cosmology and astronomy a month ago, we have decided to organize this webinar so that many of you who are stuck at home, unable to go to school, might continue the learning process. When I spoke to Dr. Sreekumar last week, actually, we agreed on making this webinar happen on Monday, the 20th of July. Since that was pretty much the day, would have been the day anniversary of the moon landings. And if you remember, yesterday is 1 year exactly from the day Chandrayaan 2 was launched from Earth. But I requested Dr. Sreekumar saying, sir, we'll do this on Thursday if you don't mind, because it'll be helpful for many people to register. I can buy 3 more days of time. But that was actually a good thing that we did, because today our department is overwhelmed with the response. We have 782 registered participants from various parts of the country for this webinar. I thank each one of you for showing your interest in this webinar and participating. And also on this occasion, I would like to ask all the participants to consider subscribing to our YouTube channel and PAC on social media, because we have a lot of exciting astronomy posts coming. So beginning the webinar, man saw the cosmos millennia ago with just his eyes, looking at the white dots that twinkled and some that didn't. He used a pair of lenses and arranged them to find out that Jupiter had moons, which was pretty much a few centuries ago. Later, in a race with himself, he started putting together his knowledge of mechanics and engineering, implementing them to build machines that left our planet to go out and study other planets. Soon, he could travel out himself, and 51 years and 3 days ago, he set foot on the moon. Today, we have machines giving us hints and possibilities of life on other planets and other solar systems. We have a probe that has left our solar system, 2 probes that have left our solar system, all because man wanted to study the sky. We have made man-made objects in space, constantly studying the cosmos, and not just out there. Space science has contributed a lot in our daily life as well. If you know the solar cells that we have today, the LASIK procedure, scratch-resistant lenses and glasses which we have on our phones right now, and insulin pumps, these were all made for spacefaring capabilities, and after being used for spacefaring capabilities, they have also been implemented in our daily life. So space science is not just limited to space, but all the advancement there will help us in daily life as well. So, making our lives easier, I welcome you all on this webinar on opportunities in space science and astronomy, where we'll learn the different opportunities that are provided to us, that we can learn, we can approach to contribute to space science, learn astronomy, and contribute to mankind as a whole. We have with us today Dr. P. Sreekumar and Mrs. Nivedita from ISRO, who will be sharing their knowledge with us today. But before I begin, I call upon our beloved principal, Dr. Raghavendra A., to deliver his presidential address. I request to all the participants on Google Meet to mute your mics and do not interfere with the presentation. Raghavendra sir, can I have you online?
Sure.
Yes sir, over to you.
Thank you, Atul. Welcome all of you. Good morning. Udupi is a land of Sri Krishna, offering namas to Lord Sri Krishna and Mukhya Prana, and seeking blessings from His Holiness Sri Sri Vishwapriya Tirtha Swamiji, the President of Adamar Mutt Education Council, one of the 8 pontiffs of Udupi Krishnamata, and is the president of Padmarmata Education Council, which governs Purnaprajna College. Purnaprajna College was established in 1960 as a foresight of founder, President Sri Udesha Tirtha Swamiji. Is celebrating its 60th year now. So we are very proud to have this program, and we have a very active club in Purnaprajna Amateur Astronomers Club. We have been witnessing all the astronomical events through this club, educating our students, local people. Recently, there was a solar eclipse in December, a full solar eclipse, and more than 3,000 people visited our college. We made arrangements. Likewise, we have traveled throughout state Karnataka, and we have educated people about this solar eclipse. So likewise, all the astronomical events have been observed here under the stewardship of founder of PAC, that's Dr. A.P. Bhatt, and now it's well led by Mr. Atul Bhatt. Space technology has got lot of importance in future. Recently, you might have seen and heard in newspapers that a chain of satellites disturbing astronomers' view. What are these satellites? See, when the government agencies, when they hesitate to invest, a private body is investing in satellites. So that will tell you the importance of space technology. India, a name in space technology, we are very proud of icon ISRO, which has contributed immensely in the field of space technology. Started initially only for space technology, now it has developed itself into an academic institute. They have also helped us in several of our programs in Purnaprajna College. They have established academic institute to spread the knowledge of space technology. So we have got lot of future for space technology, for which we do not have good number of enthusiastic students coming out seeking. So in this regard, this workshop or a seminar on what are the opportunities by a knowledgeable person, well-known Sreekumar, will be very relevant one. On behalf of Purnaprajna College, I welcome Sreekumar to address us, and we are grateful to you, sir, for sharing your knowledge among our students, not only our students, students throughout India. When we go through the applicants who have registered for this webinar, we see a large chunk is from students. So that is the relevance of this topic. Space technology, we do not have many resource persons who can talk authoritatively. So here is a person, so worth listening. So I wish you all the best, have good time and well learned time. Thank you.
Before we begin our webinar, it is my honor to introduce today's resource person, Dr. P. Sreekumar, to you all. Dr. Sreekumar is an astrophysicist by training and is currently the Satish Dhawan Professor at ISRO and the advisor to the Space Science Program Office at ISRO headquarters. After his BSc from University of Kerala and MSc in Physics from IIT Bombay, he pursued his PhD on gamma ray astronomy at the University of New Hampshire, USA. His postdoctoral research focused on the emerging area of observing the universe in gamma rays using NASA's Compton Gamma Ray Observatory. He spent a decade at NASA's Goddard Space Flight Center as a core member of the EGRET experiment. His research focused on diffuse gamma ray emission from the galaxy and in extracting the highest quality spectrum of extragalactic gamma ray background and its distribution. He returned to India in 1999 and joined ISRO Satellite Center to head their space astronomy group. He participated in the AstroSat program, coordinated the solar X-ray payload on GSAT-2, and later got deeply involved in the Chandrayaan-1 for his scientific payloads in X-ray and gamma ray experiments. From 2013 to 18, he was the director of Indian Institute of Astrophysics on deputation from ISRO, and in 2018, he rejoined ISRO as the director of Space Science Program Office, a post that he served till his superannuation in January 2020. He has been awarded the NASA Group Achievement Award, NASA GSFC Special Group Activity Award, and the Hari Om Prerit Vikram Sarabhai Research Award. Dr. Sreekumar has over 100 publications to his credit. With this, I'd like to welcome Dr. Sreekumar to this webinar, and I'd like to invite him to deliver his webinar. Before we begin, I'd like to request all participants on Google Meet to mute their microphones and disable the video for a smooth webinar, and also please do not present in between the seminar. Dr. Sreekumar, can I have you online?
Yes, thank you.
Yes.
I'm just uploading the presentation.
Yes, sir.
Bring it up to... Is it now full screen?
Yes, sir.
Okay. Thank you, Atul. I must thank the principal also for the warm words. As the principal rightly pointed out, there is expanding opportunities in this field, and the students are our focus. And ISRO certainly looks forward to stimulating as many students as possible to come in and maximally utilize the opportunities that we anticipate in the years to come. So today I would spend, the whole topic of space science research is very vast. The principal spoke about the technology component of it. I have slightly stayed away from that because there is not enough time to really cover it. So I'm going to spend the time primarily to look at the science aspects of doing science from space. So I begin with this first slide, which talks about why do we go into space to observe the universe. Going into space is not cheap. It was only made available about 70 years ago, our opportunity to go into space. So why do we do that when it's such an expensive proposition? And that is sort of shown in this figure. The top graph shows atmospheric opacity, that is the transmission, how much of light actually transmitted through the atmosphere as a function of wavelength, going all the way from gamma rays at the left to the radio at the right. What you see is this narrow little window. I hope you can see my mouse. The narrow window close to the visible, you see the spectrum that we see, is what much of humanity and much of humanity appreciates Earth because of this fact that this light, this part of the spectrum is actually transparent. The atmosphere is transparent to it. We're actually able to appreciate the things on Earth, and that drives the visible spectrum. But there are also regions in the radio which are also transparent to the atmosphere. However, a large fraction of the atmosphere, a large fraction of the electromagnetic spectrum, for example, in the submillimeter, in infrared, some small bands infrared are visible, but and beyond ultraviolet to X-rays and gamma rays are completely not transparent. So in order to study the universe at these wavelengths, you have to really go outside the atmosphere, and hence they need to use a space platform. Today, even in the visible band, we do have missions that go into space. For example, the Hubble Space Telescope that most of you would have heard of, which produces brilliant pictures because the atmosphere is not there to really cause the jitter that arises from refraction in the atmosphere. So we get very sharp images from space telescopes, even though it's expensive to operate, but the results are stunning as visible from the HST images. So space is indeed a platform to pursue the wider universe. Space is also a platform to look at our own Earth, because it allows us to have a synoptic view, a comprehensive view, and rapid coverage of parts of the Earth, which would otherwise be very difficult to really do. So the space technology has certainly impacted humanity in multiple ways. And it is very interesting to ask this question: if we were to really be in another planet, for example, like a Venus, this part of the spectrum, I've just blocked it with this blue color, because that is no longer visible, because the Venus has a lot of bright clouds that actually reflect away the solar incident spectrum, and so you can't see the surface of Venus invisible, and we're then forced to use the radio component, that's large, using radio waves to really image the surface of Venus. So clearly the atmosphere plays a big role in doing this. And a third example would be if you're on the moon, atmosphere doesn't exist, and the full spectrum is available to you, and so, which is why today people are very seriously looking at the far side of the moon, the side that doesn't face Earth, as an incredibly fantastic location to do astronomy from the far side of the moon, where the radio emission from Earth is also completely shielded. We can actually do some interesting research from the far side of the moon. So with that framework of why we need to go into space, let me now enter this field of space sciences. And here I have 4 boxes shown. These are showing the fact that we can study things as close to the nearest star, the sun, Earth, the planetary systems, and extrasolar systems. So I'll discuss each of these in turn. Sun, as you know, is an ordinary star of one of the 100 billion stars in our Milky Way galaxy. And the sun is not a steady system. It actually has large amount of plasma, magnetic fields. Internally at the center of the sun, what powers it, we today understand, is nuclear fusion processes. Hydrogen is constantly being combined from helium. And it is that release of energy from the fusion process that is slowly trickling to the top of the atmosphere of sun. What we see as a visible surface is the photosphere. The photosphere, actually, which is only 6,000 degrees, is much cooler than the interior of the sun, where the fusion processes take place. But the sun also is a rotating object. Angular momentum from the original gas cloud from which the sun and the solar system formed had a net angular momentum, which led to it being conserved by the laws of physics. And that conservation suggests when they form compact bodies like the sun, it actually would spin, and that spinning gives rise to some very complex phenomena of the sun. And since the sun is not a solid object, it doesn't spin, it has a differential spinning, so parts of the sun spin faster than other parts, and that leads to twisting of magnetic fields, and these are leading to results. These result in phenomena that we call as solar flares, when there is a huge explosion on the sun, releasing a lot of X-rays and gamma rays, and as well as ejection of plasma through a process called coronal mass ejection. So these are important processes that happen on the sun, and many of these today are affecting life on Earth and are relevant when we're looking at life elsewhere in the universe as well. So sun is not a steady object. Sun needs to be understood. Today we have many missions targeting sun. There is the most famous one, the Parker probe NASA has sent, is getting very close to the sun to really understand sun and its behavior and how it affects the interplanetary medium during its evolutionary process of 11 years. So the whole process of studying sun and its impact is what we call as heliospheric processes. So how does it, the heliosphere is this whole sphere where sun seems to influence it, and that seems to go quite a ways from where Earth is. And very recently, as Atul pointed out, there were two probes that left the solar system, and very recently we could actually see it crossing the boundary, what is called the heliopause boundary, and that is a very important achievement for humanity. Coming back to Earth, Earth as a planet is very important. It is, as we know today, only one that is supporting life as we know it, and it has an atmosphere. It has a magnetic field which protects us from the charged particles, and hence creates an environment where life can thrive. The sun, of course, provides a lot of the energy that Earth and Earth systems need to survive on. So there is a real need to do surface mapping of these surfaces. So we do that in visible, in infrared, and using radars, so that even through clouds, you can actually penetrate and actually see the surface of Earth. Radars also, at low frequency radio, can also penetrate the surface of Earth. They can actually use that to study interior, so below the visible surface of the Earth. And that's also an important thing that you can do from space. And ISRO, as you may be aware, has a very strong and solid program in actually remote sensing Earth and processes on Earth, and that has a lot of implications with regard to both in terms of resource utilization, decision making, and various other aspects where, in terms of monitoring the greenhouse gases, monitoring aerosol production, pollution levels, and a whole host of issues. Understanding the interior of Earth is very important because it is the interior of the Earth and the molten iron that we believe is out there that actually creates this field, magnetic field, which certainly is protecting us from these harmful charged particles that are actually often released by the sun. That's an important thing. So there is a lot more for us to understand the interior of the Earth. We have not been able to go very deep into the Earth. About a few kilometers is the most we've gone, but clearly there are other ways to study the interior through indirect processes of using seismology as a way to really study the interior of the Earth. But there's a lot of areas to be studied, and this study of the interior of the Earth is very crucial in understanding also interiors of other planets in our solar system. Anthropogenic effects are very critical because humans have indeed influenced the environment on Earth, and that is today a topic of great interest, and which should be of great interest to many of the young students here, because we really want to ensure Earth as a planet survives and is actually, and the beauty that we enjoy today is indeed maintained. We do know, of course, the sun is not, as I mentioned earlier, is not could undergo evolutionary processes. It is roughly half its age today. So as it ages further, it would expand, and that expanded sun could actually cause havoc to Earth. It could blow away the Earth's atmosphere. It could even completely encompass Earth. But these are things that are going to come a few billion years from now. So we don't need to worry about it right now. Going beyond Earth is our larger planetary system. And understanding its origin and evolution is critical because about 25 years ago, astronomers were successful in finding planets in orbiting stars outside the sun. That has been a major discovery. So this field of exoplanets that has now emerged suggests that nearly all stars in the galaxy might host a planet. And there are many that seems to be hosting multi-planet systems. So there is an interesting set of planets around a system called TRAPPIST-1. It is only about 40 light years away, which is a very short distance by astronomical standards, and that has multiple satellites, multiple planets, very similar to our own solar system. And these are important discoveries, and in the next many years, we anticipate this to be a major area of research and with a lot of interesting results. But one of the most interesting questions you can ask is, are these habitable, and is there life elsewhere? And this is clearly a major question for us, for humanity to answer. And we are getting closer to that. And today, while we cannot go to these planets, we can study them far away using techniques in astronomy that allows you to study, for example, the spectrum of the atmosphere, where as a parent star's light comes through the atmosphere, it actually shows absorption features, which will have signatures that are characteristic of elements and molecules that can suggest presence of oxygen, presence of ammonia, presence of other interesting biomolecules. So there is indeed an emerging area of astronomy research using exoplanets that are linked to habitability and presence of life. So these are important issues, and into that is linked this larger system of understanding the wider universe or the origin of the universe. The cosmic matter background that was discovered in the mid-1950s as a radio. Today we understand is an indication of the remnant of the Big Bang. And there are many more processes that we'd like to understand. And one of the important ones I want to point out would be this idea of universality of physical laws and its validation. Today, science and technology on Earth arises from what we observe from Earth and what we experiment on Earth, and out of which we've actually created rules and regulations, which we call as equations in physics and chemistry, processes. The question is are these universal? And is there anything special about being only on Earth elsewhere? We do believe it's universal, but proving that and understanding that is an important part of extraterrestrial research is pursued. So that background, which is sort of covers most of what we call sciences, which often we break it up into planetary sciences, that studies primarily our solar system and the influence of sun on the solar system. Atmospheric sciences, primarily Earth's atmosphere, but now we've expanded this including atmospheres of Mars, Venus, Titan, which also has an atmosphere. Astronomy, astrophysics, which looks at the sun as well as other stars in our galaxy. Extragalactic, other galaxies outside our own galaxy. Clusters of galaxies, very, very large systems that are gravitationally bound, and of course the universe as a whole. We're also now exploring other new areas of science research from space platforms into fundamental sciences. Yes. You're able to hear me well? Only the voice. Okay. I don't know. It could be some local issue. Okay. Is it okay now? Can I continue with this current slide, or things were okay? Okay. Yeah. Do point out there is issue. Huh? Okay. So in expanded area that we're now looking at is fundamental sciences, etc. And these have been made available because we now have a program of human space activities that is being planned in India. ISRO is looking at placing an Indian in space, and the Gaganyaan program, which has been initiated, has all the opportunities to do experiments that may require a human being to really interact with the experiment. And so microgravity experiments are being looked into, experiments on space biology, and of course this whole idea of biology elsewhere, detection of biomolecules is linked to this field of astrobiology. We're just starting these processes, so in the next many years, you can certainly look forward to expanded focus on these emerging areas of space biology and using microgravity to really validate things like, fluid flows, how does combustion actually in zero gravity conditions, very critical when you're looking at creation of a space station type settings, etc. So there is a lot of areas of research that are linked to space, but are connected to also basic sciences that many of you are interested in. So when you look at this pursuit of these sciences, I sort of see four broad areas that we really need to worry. Clearly, research is prime focus. We need to identify which are the focus areas. We need to have some theoretical studies that go with it. We do experimentations, do simulations, and you look at what data we exist so far. As you look forward to doing new things, and which are given by these focus areas of research, you have to then develop certain technologies because there's some technology required. Examples of these would be, for example, if you want to make directly image planets outside our solar system, the planet is such a faint object in the presence of this star, which is brilliant, intensely bright, and to really suppress the brightness of this star against which, after which you could take a picture of the planet, you would need to create what is called coronagraphy, basically create an artificial eclipse of the central star and then take a picture of that. Now, this demands very stable space platforms. And today, that is not an easy thing to do if you want to really create what are called micro or milli-arc-second stable platforms. A typical spacecraft provides a certain level of disturbances as things move on the spacecraft. We really have to create technologies that can actually stabilize it to an incredibly high level. We're also looking at satellites that are not large monolithic single systems, but an array of satellites, all talking to each other, precisely positioned, constantly ensuring that they're separated is at known level, known distance, etc. These can actually create artificially large apertures that can be very useful to do high angular resolution studies. So there's a lot of technologies that have to be really developed in the context of trying to pursue some of these focus areas of research that we talked about. And these technology and research then combines to form payloads or experiments. Payload is just a fancy term we use to really talk about science experiments on a spacecraft. And these involve design of experiments because space demands that you create very low weight systems. Every gram that you take up for a launcher is an expensive proposition. You have to invest many tens of times of grams of other parameters on the rocket and fuel, etc., to really take 1 gram into space. So you really need to ensure it's low weight, low power. There's no power. The only power we depend on is solar power. We really need to ensure that is not that is carefully utilized. So we have to create low power, low weight, and low volume, because that is also limited, and rugged. It has to survive launch, which is not a simple thing. If we have to go on the current rockets, we will not survive. That's why we're building more stable, lower vibration rocket systems for human travel. But you really eventually need to ensure payloads can survive launch, so that has to be brought in. And then they have to operate in the extreme vacuum of space. So you really need to create materials that survive such extreme conditions, extremes of heat, extremes of cold, and to really, since there is no way to go there and fix it, you have to make sure their redundancy is built into it. That is, if something goes, we anticipate possible failures and prepare for backup systems at some level. So that has to be built into every experiment that you look into. But critical to all of this, come back to what the principal suggested: human resources. We really need people working with us on these matters, and that is very, very crucial. Students have to be there, part of it on a regular basis. Who will emerge as researchers and who will pick up this whole idea of really saying, where do we need to go next? These are 4 key areas that we really need to look into. And as many of you look at your early careers, your long-term future, you need to see possible roles in any one of these areas, in the form of research, technology development, or in doing making instruments and design. So there is a lot of room for all of these issues, but resource and training. Today, as researchers, part of our responsibility is to make sure we train students and train researchers, and that is also as important as pursuing research itself. So I just thought, since there is a lot of interest in astronomy, and we can't talk about all the programs in space science in great detail, I thought I'll just flash a slide that really looks at the mega projects, the large programs, and the major programs that we're currently looking at in astronomy from India. On the left side, we've shown operational systems. We today have, going from radio astronomy to terahertz, which is in, millimeter wavelengths, visible, infrared, ultraviolet, X-rays, gamma rays, and cosmic rays. So we have a set of facilities today that are operational in India that uses, this is TACTIC, is a gamma ray telescope that the Baba Atomic Research Center operates from Mount Abu. GRAPES is a cosmic ray telescope that the Tata Institute of Fundamental Research operates at Ooty. Hagar is a telescope for gamma rays operating in Ladakh, in Hanle. MACE is a new telescope, a 20-meter telescope coming up, again set up by the Baba Atomic Research Center. And Hanle is 4.5 kilometers above sea level, one of the highest observatories in the world. In the area of X-rays and ultraviolet, we have a satellite currently orbiting ISRO satellite called AstroSat. That's will complete 5 years in September, operating very well, providing in ultraviolet the sharpest pictures that has ever been obtained with a wide field condition. So we have a very, very good satellite producing a lot of interesting results called AstroSat. In the visible, we have ground-based facilities, various large number of telescopes. The largest one today is a 3.6 telescope located near Nainital, a place called Dhawan, optical telescope operated by the Aries Research Institute, the Aryabhatta Research Institute in Nainital. And then at radio, we have the Ooty Radio Telescope, a brilliant concept that we put together many years ago. Later followed by the Giant Meter Radio Telescope, one of the largest low-frequency telescopes in the world, operating near Pune. And at very low frequencies, there is the Gauri Bedinur Radio Telescope in Gauri Bedinur in Karnataka, which actually is very, very important to study the sun. It actually looks at a few hundred megahertz emission coming from the sun. Whenever the sun there are explosions on the sun, it actually shows interesting signatures that are studied on a regular basis. Now, when you look into the planned program for the future, you have a few satellites that are coming up next year. There's a polarization satellite or X-ray polarimetry satellite. This is coming after many decades of a gap. The first X-ray polarization satellite is being launched by ISRO next year. The Raman Research Institute is leading the experiment here. There is a big mission to look at the sun called Aditya that actually creates artificial corona on the spacecraft to study the corona of the sun. The corona, as you know, can be best studied during an eclipse, but that only happens very rarely. So we actually build a satellite that can make a corona all the time and study the corona and use that to study emission from the sun as like a coronal mass ejection. And that is being planned to be positioned in a interesting location called Lagrange point 1. Now, these Lagrange points are whenever you have two body systems and they're rotating, you can actually create stable potential points where the gravitational pulls are balanced by the Earth and the Sun, and that is a great location for the spacecraft to sit. And so Aditya L1 would actually be taken to Lagrange point 1, the first attempt by ISRO to really put it in L1. Looking beyond that, we have a series of satellites that are looking at the gravitational wave. Some of you would have heard about this gravitational wave detection in 2015, after 100 years, something that Einstein did, but it took us a long time to get to it. And today, we see gravitational waves are rising whenever very intense emission, when very, very compact objects like, yeah. That needs to be okay. Sorry. But I can't disable the video, right? Oh, no. Okay, I did it. Okay. All right. I guess that's the slide. Where'd my slide go? How do I get back? I know I am not able to see the slide. That's my problem. So I don't know which slide I'm on. I'm surprisingly not seeing the slideshow part of it. All right, 1 second. Is it visible now? Okay. So, okay, thank you. So I was just discussing this planned programs, and there are a series of satellite missions under consideration. These are not yet confirmed, but we're looking at this mission that would look at so I was talking about the gravitational wave detection that LIGO has detected, and there is a new European, well, it's been there for some time. Virgo is a new European gravitational wave detector. There's another one coming up in Japan called Kagra. And as some of you may be aware, there's one coming in India, but that will be 2025, 26 when it actually is ready to take data. So we are looking at one of the problems with LIGO is it doesn't give you very good position as to where this gravitational wave has come from. So one idea is to look at it and see if we can see an electromagnetic signature, something, there is a flash that goes off in X-rays at that time, then we'll be able to catch it. So we're looking at an mission called Daksha that actually attempts to really catch this flash. So that is one of the missions being considered. There is a large ultraviolet spectroscopy mission being considered, maybe in collaboration with Canada. And there is also a large emitter, and also a mission that looks at called exoworlds, that is actually trying to look at the atmosphere of exoplanets. So, and there are again new technologies on terahertz, which is a completely new area of work. We are now exploring the possibility of a terahertz mission, which is really interesting for Earth sciences as astronomy, which shows some of the coldest atoms in the universe to be studied with terahertz. It's also very important to look for biomolecules. Terahertz is a very interesting place to look for biomolecule signatures. This is just to indicate to you there is a huge array of things out there for us to do. And if you are limited in one front, I would say that is in human resources. So that's where all of you come in. Oh, sorry, just before that, I also want to show you at the bottom, there are these mega projects that are also running. Government of India has been funding these programs. The 30-meter telescope, India has a 10% share in it. 30-meter, it's a huge program. The Square Kilometer Array, the largest radio telescope in the world, India is partner in that. LIGO India, where India is setting up this LIGO mission as well. And then there are, of course, a few more things coming up called the CTA, the Cherenkov Telescope Array and Gamma Rays, the Large Solar Telescope in Ladakh, and a large optical telescope being planned in India. And maybe many years from now, we might think about a space gravitational wave mission. There are a few people discussing this quietly when the lights are off and when after sunset. So we need to expand the discussion, and these are all possibilities for the future. So this is just on the leftmost side, you will see this theme. Just for astronomy, you're looking at planets and habitability, solar physics, stellar physics, end state of stellar evolution, active galaxies, quasars, transient astronomy, things that go off in a flash and whose brightness lasts only for a short period of time, and surveys of the sky, looking for all exoplanets in the sky, things like that, and early universe studies. So there's a variety of things that we are planning spread across these decades of 2025, 30, and beyond 2030. As some of you will be aware, these are all very challenging missions. What we plan for a few years often ends up being many more, but that's because these are challenging, difficult. Many things have to come together for the success of these missions. Now let's come to some opportunities for students. So while you are a student, my suggestion would be that you can focus on these four things. Outside, of course, your classroom, your regular curriculum that you have to really work on. One is to really develop what I call analytical skills. How you look at a problem. How do you break down a problem? If there is a crisis, then how do you tackle it? These are things that are usually very well taught from a college program, and your teachers would be addressing that in many different ways. But important thing is to really be able to really derive or improve the skills that you have on looking at a problem analytically, which really also requires fresh thinking and independent thinking. You may be told something, but that doesn't. You should go home and try to tell that to your parents or to your friends. And when you try to tell them what you thought you understood, you suddenly realize I don't fully understand it. And but by the time you learn to say it correctly, you would have actually developed certain analytical skills. Experimental skills, very important. You want to build things. Often we say a theoretician can write up something, and if I have a spherical cow, I can then define what is the mass of the cow, etc. But the real cow is very different, and you really need to know how to do real systems. And so experimental skills are critical, and you have to really build expertise in analysis methodologies. How do you look at data? Data today is what the universe, the world is filled with. Data analysts are in great demand, and how do you look at data? And that requires a mathematical framework, requires bringing in the analytical elements, it requires putting in errors in every measurement that comes from the experimental skills. So analysis of data is very critical. And of course, that is made possible by computational tools. You must learn computational tools. And that doesn't mean learning to use a PowerPoint or a Word, but actually how to calculate, how to really simulate, how to really speed up certain things. And these are quite possible. And one of the most powerful tools that today is out there, and it's so easy to learn, is Python. If all of you learn Python, I think it is sort of like the early saying, instead of giving someone fish when somebody is hungry, teach them how to fish. Today, I would say, teach them how to do Python. And you'll really go quite a ways with learning how to do programming in Python. So the approach for you would be to define a problem analytically. We define equations that define the problem in some cases. We calculate for certain conditions, how does the system behave using some standard inputs. You know, if you were to ask the question, why would Earth be a comfortable place to live, but Venus is not, you would have to really put in initial conditions and then see and let your simulation run and see what actually happened to it at the end of a certain period of time. This data that comes out has to be plotted. You have to look at it in different ways. That is where your computational skills come in. I need to draw some conclusions, improve upon the requirements for the next iteration. Science never stops. We keep improving, and that improvement comes when you draw conclusions, understand limitation of the previous experiment, and feed it back to design. And this is an important part that we all have to do. And that is what makes science so interesting to pursue. Let me take a few concrete examples. One is, here I'm trying to give an example of something we did on Chandrayaan-1 and Chandrayaan-2, that is to detect elements on the moon. One of the key things about the moon's surface, we wonder, is what is its composition? What are the minerals present there? Minerals can be studied using, looking at the absorption in the solar light that reflects off the surface of the moon. When it reflects on the surface of the moon, the minerals on the surface will absorb some of it, and so you'll see a difference between incident solar light and the reflected solar light. Another way to do that is to look at when there are X-rays coming from the sun, they actually would excite atoms to higher energies, and then when they de-excite, they will give rise to an X-ray signature that's very specific to a given atom. When you go to a goldsmith shop these days and you say, I have some old gold, they'll put it under a machine and very quickly tell you within a matter of a few seconds how much copper is in the gold. And the process of doing that is nothing but X-ray fluorescence, where you allow X-rays to fall on it and return the signatures of gold and copper comes out very, very quickly. We do something very similar on the moon. We allow the sun to fall, sunlight during when the sun undergoes a flare, a solar flare. X-rays are produced. These X-rays fall on the surface of the moon, and those X-rays will actually excite atoms of sodium, potassium, magnesium, aluminum, silicon, titanium, iron, and so on, sulfur. And we can actually pick this up from an orbit 100 kilometers away. So you have to really build a sensitive instrument. So today on Chandrayaan-2, we have a very sensitive, maybe the world's largest X-ray instrument that has been flown to the moon, which actually is attempting to derive abundance of elements from the surface. So we understand the goal, we have a set of a principle of how we'll do it, we create a detection method. There are many ways to detect it. We chose, in this case, X-ray fluorescence. Then what do we do? First step would be to identify, we need something to excite the atom. So we now realize we could carry an X-ray generator with us, but that is heavy, consumes a lot of power, and you cannot shine those X-rays from a 100-kilometer orbit and expect that to excite the atoms on the surface of the moon. So we instead use sun itself, nature itself, during solar flare. So we wait for sun to undergo explosion, constantly watching the surface of the sun, of the moon. So we identify the excitation source. Second, we design a large enough detector to get adequate signal within a short time. Sorry, I said short time. Because you're orbiting, right? If you want to, you are orbiting at a rate of about 1.5 kilometers a second. So now if you want to really derive something at the level of 10 kilometers, you want to know what is the dominant elements in a 10-kilometer patch, you have to make sure that in 1 second you get enough signal. And that means you have to really, and remember you're sitting 100 kilometers away and the X-rays are coming from the sun. So it's really a challenging thing. It's not like the goldsmith shop where the X-ray source is sitting right over the piece of gold. So quite a challenge. And you have to estimate how many X-ray photons of a given energy are produced for a given solar flare. The flare is also not steady. We don't know when it'll come. All those are challenges when you're trying to do this in in-field conditions, in actual remote sensing conditions. The step 3 would be to explore sensitivity of these measurements and uncertainties. When we design the instrument, I need to know what could be things that could cloud it, that could make these measurements difficult. One is background. If I have a lot of optical photons, light itself, it can actually destroy, the sensor could actually get saturated. So you create a cover on top of it that actually cuts off the optical light. Detector produces background, so you need to measure all this. Sometimes temperatures will change the gain, which means your identification of the element can shift. So I need to worry about the calibration of that stuff. All these are critical issues that we need to pay attention to. Step number 4, develop algorithms. Now I get the data. Now I need to make sense out of it. I see some spectrum, but I need to make sense of it. I need to develop algorithms to derive abundance from the measured counts. So this is an inversion process that every data system requires. Any measurement to science or any measurement to what you're fundamentally looking for demands inversion algorithm. These are non-trivial typically, and you have to really do this, and sometimes to really test these algorithms you have to do tests in the lab. So there is a whole host of activities you can have in a laboratory where you actually test whether these algorithms are good. Is the emission correct? So for example, when we are doing this experiment on Chandrayaan-1, that was the time when the RBI, Reserve Bank of India, was actually producing this new 10 rupee coins. I remember we got one of the first 10 rupee coins and actually took it to the lab in ISRO Satellite Center and actually put X-rays on top of it, and then put a return signal. And I had a student whom I tell him what it was made of, and his job was really to tell me what is this composition, and we could actually show that we are indeed getting useful results. So laboratory testing is a critical part of any of these experiments. And then finally, of course, conclude and plan for the next level of improvement. What we did on Chandrayaan-1, we expanded and made it better on Chandrayaan-2. So this is just to give you a concrete example of how these things work. And a second example that time permits is here is a plot of what I call a sulfur dioxide measurements in Venus. Venus is a very complex place. We don't have to discuss that in great detail, but Venus has the atmosphere that is full of CO2, about 96% is CO2, and there's also sulfur dioxide. One of the things that has been observed in the last many years is this SO2 level keeps changing. So here is a plot that shows over the years, 1980 to 2010. There's a gap because there was no Venus mission at the time. But you see SO2 levels changing, sometimes goes up, comes down, again it goes up and comes down. We still do not know what it is. And so the idea is it could even be volcanoes, that because so much of Earth's sulfur comes from volcanoes, could be seismic activities. But what you see, we have is observation, and you need to make sense of these stuff. We believe because these clouds of Venus also has sulfuric acid. And that is, we believe, comes from this process under which where carbon dioxide is actually dissociated, broken, where you have atomic oxygen produced when light from the sun, often ultraviolet or even visible, can actually create this. And this atomic oxygen is very reactive, and that can react with SO2, forming SO3. SO3 combines with the water vapor, forming in the intermediate molecule, and then finally H2SO4, which condense in these clouds that actually are reflecting huge amount of sunlight from the top of sunlight coming from outside is reflected away, which is why Venus is so bright. So to understand this, we have to go through the whole process of, again, walking through this process of what is producing, what are the sources and sinks of sulfur, what is the light that's coming in. And so the process of understanding SO2 would be to really look at all these different processes that are participating in this exercise. So let me close with some final remarks. Space science research, I believe, is exciting, and I hope I've been able to convey that to you in some sense. And India has a very strong program in place to offer you new and unique opportunities. It could be stronger with your participation for sure. Your pursuit of experimental or theoretical or maybe analysis that is heavy in data are critical. Sometimes it also includes modeling efforts. They give you different perspectives on these things. But each of them often typically we specialize in one or two of these, and that gives you opportunities towards a career that is widespread. It could be, for example, someone who is involved in doing theory, involved in analytical views of the problem, mathematical framework, and then they can help you calculate outcomes, make predictions using equations, etc. Theory is very critical. Some of you may be inclined to doing that. Experimental work will expose you to design and calibration of instruments, gives you a good background for instrument design, any instrument design, I would say. Understand measurement uncertainties is a very crucial thing that makes you a good experimentalist. Validate theoretical predictions and often reveal new findings. You go with a new instrument and you see something that you never saw before. Analysis, data analysis is crucial in understanding and the data. So you use a lot of interesting mathematical tools. And these tools can be of great exposure. People who solve some of these problems, also solve how the stock market goes up and down, banking industries and global warming, in a number of places. So this area is very powerful if you really have a good background in it. And that's very important for the emerging area of data analytics, which is very, very, very critical. And many of you might find that very exciting. And finally, in terms of simulations, often we simulate what we expect to see. Today, before we build instruments, we simulate. Let us see what it would look like. And that is driven by computer-based models, and also uses data from other missions, etc. And that's how we actually build some of these things. So this, as you can see, offers a variety of opportunities, and I hope many of you will exploit that and will become a major resource for the country to utilize your strength in taking us much further in the area of space science research. Thank you. Oh, sorry, I was muted. Sorry, I got the question. Okay. So what I was saying is, for a career in this, it's important to really pursue advanced studies. So as an undergraduate student, you really need to be looking at master's and PhD programs that encompasses and ensures that you have a solid foundation in mathematics, physics, chemistry, and as I was mentioning, even in biology. Space biology is the emerging area. And if you look in terms of just astronomy itself, I can say, for example, our ISRO has an institute in Trivandrum called IIST, which has an MS program. It's a combined program, MS program, 5-year program in astronomy and astrophysics and in earth sciences. Osmani University has an MS in astronomy, and there are astronomy electives being offered under physics department at Bangalore University, Pondicherry, I think Delhi University has, Pandit Ravi Shankar Shukla University in Raipur. Many such places are there. And at the PhD level, you have institutions like UCA in Pune, IIA in Bangalore, RRI in Bangalore, TIFR in both Bombay, Mumbai, Hyderabad, and in Bangalore. ICTS, the Center for Theoretical Sciences here in Bangalore, ARIES in Nainital, IIST in Trivandrum, PRL in Ahmedabad, and so on. So a fair number of them. Now, over and above that, there's another interesting thing that the Institute of Astrophysics has a unique program in combination with the University of Calcutta that actually offers for engineering students an MTech program followed by a PhD in technology and astronomical instrumentation. It's a very unique program. It's been running for more than 10 years. And what we see is engineering students with interest in sciences come into it, and they were involved in actually design and development of major instruments and major experiments, and many of them are now involved in our leading mega projects like the TM 30-meter telescope and LIGO India projects. So it offers a lot of it, and that area of mathematical sciences SC University has a big program. The Space Laboratory in the SSD has a big program. We have a National Atmospheric Research Laboratory in Ranki, PRL, etc. So we have a wide set of places, but core is making sure your basic sciences are indeed addressed.
Okay,
Hello,
sir.
Hello,
Yes.
sir. I am audible. I'm
Yes.
audible. Sir, I have some question. I am MSc student from Udupi. Uh, for my project, how can I get some data from radio telescope?
Radio telescope data is always available today, even on the National Center for Radio Astrophysics in Pune. Their web page itself, you can, from the archive, you can get a lot of radio data. Also, there is radio data available in a huge number of things on the internet. Many radio astronomy, like the Very Large Array in the US, etc. Radio data is available. What is useful, of course, is to know specifically what area of radio data, what type of radio data you need. Accordingly, you can download it from such places.
Sir, I have also another question. You told spinning of sun that leads to change in magnetic field, right? That is very complicated to imagine. Actually, my question is, what is the actual reason for sunspot, and why sunspot disappear 1 of 11
We understand that fairly well now, and you can certainly, after I tell you, can go back and look at some of the available information on the internet. But primarily, to give a very short answer, you can think of the sun as a solar gas, and you imagine a lot of magnetic field lines immersed in it, falling down like rain. Now you start spinning the sun, with the equator spinning faster than the poles. What will happen is, the magnetic field is carried by the plasma also, and so at the equator of the sun, the magnetic field will get twisted more than at the poles. And when this twist becomes substantial, it emerges from the inside of the sun to the outside, and those spots which are now strong in magnetic fields, but little cooler in temperature, is what we call as a sunspot. Okay.
Sir, there are a few questions on the chat, and the question is actually by Yuvashri that other than Python, are there any important computational skills required for astrophysics career? Since you've mentioned gain, calibration, and algorithms, there's a lot of computational data in the research.
Sure.
So, what would be a computer student's forte to join and get into space?
I mean, it's a combination of physics, mathematics, and computer science. Computer programming is that what you have to really put together. So you have tools like, for example, even the engineering side, digital processing, fast Fourier transforms, which to really do, filtering of data. Filtering of data is something we have to do. Data that you typically get from instruments is a mess. The cleverness in with which you pull the signal out of that amongst all this noise is what is called filtering. And that filtering today, for example, the gravitational wave signature that was seen by LIGO is brought out by a principle called match filtering, and where you simply do a blind search and ask, can you show me, I know what the pattern will look like, and it does a very fast search for these things. There are many techniques that are common to engineering and sciences that you need to learn. And then there are tools that are there where you can implement these techniques very quickly. That is where Python comes in, because you can borrow from a library that exists out there. Much of it as coding has actually been done. You just have to put it all together, quickly redo it. If you want to, for example, do automatic tracking or identification of craters on the moon, there are algorithms out there in Python and in the open source condition that you can pull in, and maybe by tomorrow you'll be able to really create a tool for automatic crater tracking. So it comes in from various areas. So there is techniques like that, and there are tools like R, another programming language, which actually allows you to do this by using statistical techniques. So statistical analysis of data is also crucial. So it's a combination of all of this that really leads to, but these things will evolve, and you need to be up to date with regard to the strengths and weaknesses of new things that are emerging.
Okay.
I think Nivedita suggested something. Nivedita, I missed what you showed.
She's answering questions from the students. She's
Okay.
So all the students asking questions regarding career at ISRO, Nivedita ma'am is busy answering
Sir,
them.
I am answering some of the generic questions.
Okay, thank you.
Sir, I just have one more thing to ask from the question that given that SpaceX is now famous in US, we also have emerging private companies in India. So right now, when we say space science, most of our students think of ISRO. But what do you think about the private companies in India, and what may be the opportunities that our students may get there?
I mean, as you rightly said, there is a need to really look at private player, and we have always been looking at private players. As often stated, today our rockets, a large fraction of it, 7%, is contributed by private players. But a private player playing a supporting role is different from a private player leading a program. SpaceX today has reached that stage. So we certainly all needs to get there, and we really need to get into that as well. What is key is these are expensive propositions. If you look at all the big players and private players globally, they're all backed by billionaires who have infinite amount of money and who can actually seem to be willing to take high risk. We don't have too many of those in India. So our industry, as it slowly emerges, where they're willing to take risk, they're willing to do planning under which we say, I will get my profit 15 years from now, not now, willing to be patient. I see the emergence of big private players in the country. But immediately what we hope to see is a large involvement of private players in many of the programs that we now do, including, as was emphasized by the government, in planetary exploration. So tomorrow, if somebody has to fly a balloon in the atmosphere of Venus, we hope a private partner will come and actually give us a balloon for that, or build small experiments that can be done, or a sensor that can come from private players, etc. So I think we are at the early phase of that, and some great opportunities for that to emerge. But it's risky. You need to enter it with great caution. Those who have startups will tell you how risky a startup is, but that's challenge, right? Really willing to take risk at this early phase. So I think the prospects are very high.
Yes, sir. So many of the questions have already been answered. They're asking if chemistry is involved and coding is involved. So it's already answered them very beautifully that you need a lot of, you need to be good at physics, chemistry, and all these fields are involved in space science. I'd like to inform all the participants that the questions that are not answered, you can mail them at askpac, ASKPAAC at gmail.com, and we will make sure we get them answered by resource persons like Dr. Sreekumar and Nivedita ma'am. We will call it an end to the discussion session since it's already 11. Participants, please note the feedback link will be displayed at the end of the chat on the screen after the vote of thanks. You can also follow PAC on Instagram and Facebook, and for our astronomy updates. We will host future programs like this. So if you are interested, please do follow us and subscribe to our channel. We will call it the end of this webinar. I will now call Mrs. Pratibha Acharya, Head of the Department of Physics, to deliver the vote of thanks for this program. Pratibha ma'am, are you online?
Yes, Satish, sir.
Yes, please continue.
Can I add this?
Yes ma'am, yes ma'am.
Good morning to all. Sir, Sreekumar, good morning, sir.
Thank you.
The Department of Physics at ISRO has always had great success with programs because of the support it has received time and again from scientific community, members of public, media, faculty members, participants, and students. So I take this opportunity to thank all of the participants and resource persons with the blessings of Lord Krishna and Mukhya Prana and His Holiness Sri Vibhudesha Tirtha Swamiji, founder AMEC, that is Adman Math Education Council, and present President, His Holiness Sri Vishwapriya Tirtha Swamiji, present President AMEC, and His Holiness Sri Ishapriya Tirtha Swamiji, Vice President AMEC. This is another such program which has been a success due to the amount of time and effort put in by every single person here. And I, Pratibha Acharya, Head of the Department of Physics at Pune Prajna College, would like to thank all of you for your contribution. First and foremost, I extend our sincere gratitude to Dr. Sreekumar, our speaker for this session, for taking time off his busy schedule and agreeing to do this webinar and delivering such a wonderful talk. So I am sure your personality and words have made a huge impact in all our attendees. Thank you, sir. Thank you so much.
Thank you.
Secondly, our heartfelt thanks to Ms. Nivedita BK from ISRO, without whom this program would not be a reality. From helping us to organize this program, being a constant support and making time for us and taking part in the discussion program. So you have always been a source of inspiration for us, ma'am. Thank you. Thank you so much, ma'am. I would also like to thank our beloved principal, Dr. Raghavendra, who has always extended support to the department in any program we organize, and for his constant guidance will be given in the future also. In all its endeavors, the department has always received support from the members of the management, teaching and non-teaching staff of our college who have helped us in this program. So the members of the Department of Physics have always worked hard in making such program happen, and it is their hard work and effort that makes such innovative programs a reality. I would like to thank all the members of my department and the supporting staff for their effort in making this webinar happen. And my special thanks to Mr. Atul Bhatt, coordinator of PAC, who have initiated the idea of conducting such programs. Last but not in no way the least, all the participants from Jammu, Kashmir to Tamil Nadu, from Gujarat to Arunachal Pradesh and all places in between, you have shown up in large numbers and have taken part in this webinar and discussion patiently and helped us to manage this event smoothly. I thank you, each one of you, for your participation and for showing us that such topics unite us all in our curiosity and learning. Thank you one and all.
Thank you, ma'am. Thank you, ma'am. Thank you for leading the... Yeah, ma'am. Yes, ma'am. Thank you, ma'am. Thank you so much for joining us. Dear participants, please note the feedback link has been posted to the chat on both the platforms. People on YouTube can see the link as well. Feedback link will be online till 1 p.m. today, so please make sure you leave your honest feedback and do follow back for all our future programs. Thank you one and all. Thank you, sir. Thank you, ma'am. Thank you, everyone.